So it is my great pleasure to introduce Glen Cowan as our STEMS webinar speaker this month. So Glen is an experimental particle physicist who specializes in statistical methods for Heinze physics. So he's based at the Royal Holloway University in London. And he has been there since 1998 as a faculty member. He got his PhD in 1988 from UC Berkeley, and then he did a couple of postdocs, and then he joined Royal Holloway. He works on experiments at the Large Hadron Collider at CERN, I believe mostly at the ATLAS experiment, and he's one of the leading experts in statistics for Heinze physics. And in fact, one of the things he's also very well known is the lectures he gives on statistics. It seems that almost every year he gives this big sort of series of lectures on statistics at CERN. And in fact, even myself, I actually attended Glen's lectures as a student at CERN many years ago. So in addition to all the research impact, I think Glen has done a tremendous sort of work for the community in introducing statistical methods to many cohorts of particle physicists. So that has been a great impact for the community. But with that, let's move on to the talk today. So today, Glen is going to talk about this problem of errors on errors. So the title is Errors on Errors, Refining Particle Physics Analyses with the Gamma Variance Model. So Glen, please go ahead.
All right. Thanks very much, Mikhail, for the introduction, and thanks for the invitation. It's a pleasure to be with you today, this evening. As advertised, I'm going to talk about a type of a statistical model that has parameters that characterize uncertainties or errors. And oops, let's see if this is going to work. There we go. This is the cartoon version of what I'm all on about here, is that in physics in general, we have to measure things and we have to assign error bars to those measurements. And sometimes the values that we assign to the error bars also have errors. And in contrast to the cartoon, I'm not going to continue that procedure ad infinitum, but I do want to talk about a type of a model where we characterize, where we bring the uncertainties on the assigned uncertainties into the model. That's the basic idea. So I will start with some motivation for why one would want to do such a crazy thing. And I will talk about how things have been done basically in physics up to now, where you treat the error bars that you assign as fixed constants, basically. And then I'll introduce this model where the variance parameters are treated as adjustable parameters. And then I'll show some of the properties of the inference that emerge from that type of a model, the type of confidence intervals you get, the way to characterize goodness of fit, and so forth. And then just a few months ago, I applied this type of a model to a recent measurement of a quantity called the muon anomalous magnetic moment, the muon G-2. And this is a quantity that, well, I'll get to that when the time comes. All right, so this is based primarily on a paper that is now 2 years old. And there have been a few intervening developments, but that is the primary reference for the material that I'm going to show. All right, so here is a typical particle physics measurement as we know and love it. You measure some set of quantities that I'm calling here the vector y. And that is characterized by some probability model that contains parameters of interest mu and nuisance parameters theta. We need to somehow provide some information to constrain the values of the nuisance parameters. And so the most common scenario is that we might have some direct estimates of the nuisance parameters, and I'll call those u. So I'm writing these as vectors in the sense that ui is going to be a Gaussian distributed estimate of theta I. And I want to suppose, as is usually the case, that these estimates of the nuisance parameters are independent. And what people would assume prior to my prodding them to do otherwise would be that these estimates U would have some known standard deviations, sigma U. All right, so the likelihood function that you would write down would just have the part referring to the primary measurements Y, and then these independent auxiliary measurements or control measurements U. And as I said, I'm going to consider the case where these U sub i's are independent and Gaussian distributed. Okay, so the log likelihood then up to an additive constant is just the normal log likelihood from the primary measurements, plus this set of this sum of quadratic terms. And okay, sometimes called a constraint term in particle physics, although that's maybe a bit of a misnomer. In any case, that assumes that the sigma ui's are known. Now, because these control measurements are there to constrain some sort of systematic uncertainty in the model, if you didn't have the nuisance parameter, the sigma ui's are what I'm going to call the systematic errors within the measurement. That term systematic error in physics gets used sometimes in slightly different ways, but in the present context, it's these standard deviations of the auxiliary measurements that I'm referring to as the systematic errors. All right, so now, very often the inference that you wind up making about the parameters of interest turns out being sensitive to the values that you assign to these systematic errors. But those values are themselves uncertain. Hence this notion of errors on errors, or I should really be saying maybe uncertainties on uncertainties, but that's just too many syllables. So what do you do in that case? Well, what the community has, I think, traditionally done is that if they're a little bit uncertain about the value to assign to one of the sigma u's, they would just inflate it a little bit. But that turns out not to be sufficient, particularly in circumstances when you're trying to average values and perhaps these values are not themselves internally consistent. So this need for putting the error bars on your error bars becomes most visible when the input data into your analysis has a sort of internal inconsistency. And so this occurs when we're trying to combine the results from different measurements. Maybe the two experiments are not completely consistent. It comes up whenever the systematic error, the sigma u, is assigned not by some principled procedure, but by some sort of ad hoc recipe or some guess. All right, so anytime when these sigma u's, the so-called systematic errors, are uncertain, that is going to be fair game for this type of model that I'm going to discuss. So one of the important applications for this type of procedure is when you're just using the method of least squares to try to average different measurements of the same fundamental quantities. And this is something that we have a long tradition of in particle physics. And at least in the modern era, I think it starts with this paper here by Raymond Burge in 1929, where he published this compendium of average values of what at the time were the fundamental constants of nature, like the speed of light and Newton's gravitational constant and so forth. So this is the forerunner. This paper is the forerunner of what became the particle data group, which is this group still based in Berkeley that coordinates averages of different measurements. So here's one of the problems that immediately occurs in that type of enterprise. Maybe you have two different groups that have measured a particular quantity, and one comes up with a value of 9 plus or minus 1, and the other finds 11 plus or minus 1. And so you average them and you get 10 plus or minus 1 over root 2. On the other hand, you might have a situation where one group finds 5 plus or minus 1 and the other finds 15 plus or minus 1. And so you still have then, if you do this average just with ordinary least squares, you'd still have 10 plus or minus 0.71. So the length of the confidence interval for the parameter of interest, for the mean, is insensitive to the internal consistency of the values that you're trying to average. So that's a problem that we need to somehow address. All right, so let me just make a few more comments on when and under what circumstances the sigma u's could be uncertain. Sometimes the control measurement is a separate measurement, and the sigma u reflects a standard deviation related to the sample size of the control measurement. Now, if that's the case, then the sigma u itself is probably quite well estimated, and this whole thing is not really relevant. But on the other times, the control measurements, the auxiliary measurements, are from some other measurement, perhaps for which the Gaussian model is only approximate, and it could be that the sigma u's that you want to assign are not directly relatable to some sample size, so their values are not exactly known. And then in the worst case, but which comes up and is very relevant for us, is when you have perhaps a nuisance parameter that appears in a theoretical prediction. And so really what you have is an uncertainty that relates to perhaps some mathematical approximation that has been made in deriving the model prediction. So if some of you perhaps joined this meeting last week, the phi-stat meeting, and there was quite a bit of discussion on this type of uncertainty. We need to make a prediction for the underlying model based perhaps on perturbation theory to some limited order. Are there any number of mathematical approximations that might enter into the model prediction? And so the uncertainty in that model prediction, at best, we have some sort of vague guess to the value. And so I hope it's not a controversial statement that the systematic errors that we assign in general will not be known with perfect accuracy. So if their values are uncertain, let them be adjustable nuisance parameters in the model. And take the numbers that you would have normally assigned to them and treat it as fixed constants, and treat those as estimates of those nuisance parameters. All right, so I've basically just doubled the number of nuisance parameters in the model, because now for every control measurement, I said that its variance is now a nuisance parameter. So that's might turn out to be a headache, but it turns out not to be such a big problem. So I could say, for example, that what I previously wrote down for sigma ui, I'll call that SI, and I'll treat that as an estimate of the parameter sigma ui. It turns out that in the model, it's much easier to deal with variances rather than standard deviations. And so from here, I'm going to just define V as SI squared, and I'll take that as an estimate of sigma ui squared. And then I will model these VIs as independent and gamma distributed. Now, I could have picked really almost any type of a distribution, any sort of reasonable bell-shaped curve to characterize the uncertainty in my estimate of the sigma u squared. And I tried a number of different ones. I mean, I tried log normal and so forth. As long as you have some reasonable bell-shaped curve, then actually the important properties of the model are all very similar. But I'll explain in just a little bit why the gamma distribution for the estimated variances turns out to be a very nice model. So anyway, there's the gamma distribution, and the expectation variance are written in terms traditionally of these parameters alpha and beta. So the idea then is to choose those parameters so that they give you a gamma distribution that reflects the appropriate relative uncertainty in the parameter sigma u. And what we'll see that this leads to is a model that is equivalent to replacing the Gaussian distribution for the UIs by a corresponding student's T model. And the number of degrees of freedom of the student's T is going to be related to a parameter that I realize now I haven't defined yet, this little r, and I'll define that in just a second. It's related to the relative error on the error. All right, so let me make a few more comments on why I think the gamma distribution is an appropriate model for the estimates of the variances. If you actually had a sample of n independent observations of these auxiliary measurements u, then if you looked at the sample variance from those n observations, then the estimator from that would be gamma distributed. And the alpha and beta would be related by these the formulas here. So that's now, but in general, you don't actually have a sample of values u. You have one value u that represents your estimator of the corresponding nuisance parameter. But nevertheless, that makes it plausible that a gamma distribution is a reasonable model for an estimator for a variance. But now the real reason why I prefer the gamma model for the variance is that it allows one to profile over these nuisance parameters, the new nuisance parameters sigma u squared, in closed form. So you don't actually double the number of nuisance parameters in the model. You can profile over them in closed form, and it leads to a very simple profile likelihood. Okay. All right. So now this parameter little r that I forgot to define, that the alpha and beta traditionally used to describe the gamma distribution. I can relate those to the sigma u, all right, and to this parameter that I call little r. And little r for the ith measurement, I define as 1/2 of the variance of v, the estimator for the sigma squared, divided by its expectation value. And then to first approximation, that is the standard deviation of the estimate of the standard deviation divided by the standard deviation itself. So it's like the relative error on the error. It's the standard deviation of the estimate of the standard deviation in relative terms. And so that's the number which I wanted to define in that way so that it would be relatively straightforward to elicit a value from somebody who did the auxiliary measurement. So you could say, all right, you've estimated this nuisance parameter, and you've said you've estimated it with a certain error bar. I could then ask, well, how accurately do you think you know the error bar that you just told me? Do you know it to 10%, 20%, 30%? All right, and so then I would know to write down 0.2, 0.3, and so forth for the parameter little r. So that's a fixed hyperparameter that the analyst has to be able to assign a meaningful value to by interrogating the expert who did the auxiliary measurement. And so anyway, there's the gamma distribution for different values of this little r. In terms of the intuition of the person who did the auxiliary measurement, they will have more intuition for the standard deviation rather than the variance. And so if you translate that, here's the distribution of the estimate of the variance. That's actually not a gamma distribution, that's a Nakagami distribution. So anyway, you could show that family of curves to the expert and say, all right, which one of these curves best reflects your notion of how accurately you assigned your error bar? And you say, oh, the blue one. So, okay, fine, little r is 0.1. All right. So given those ingredients, we can now write down the full likelihood function for the model. So it's got the part that relates to the primary measurements, and then this product of Gaussians that describes the auxiliary measurements, right, that estimate the nuisance parameters theta I, and then the product of gamma distributions that relates to the estimates v of the sigma ui squared values. And then here I've written this still in terms of the alpha I and beta I, but I remind you that they are related to sigma ui squared and this all important parameter little ri. Okay, so there's just a summary of all the ingredients. All right, so as I mentioned, the beauty of that particular form is that you can profile over these sigma ui values in closed form. And so the values that maximize the likelihood for fixed values of theta and mu are given here. Right? And so that allows one to write down a very simple equation for the profile likelihood. So when I say profile log likelihood, I mean profile now only over the sigma u squared. It's not over the other nuisance parameters theta. And so what happens then is that what were previously a set of quadratic terms now become logarithmic terms. And you can easily see that in the limit that you claim that you know the values of the assigned systematic errors accurately. So in the limit of small little ri, then if you expand the log, you can easily see that that reverts back to the sum of quadratic terms that was there previously. All right. Now, as I'm sure the statisticians in the audience have recognized, this is equivalent to a student's T model. All right, this is the same as if you were to say, instead of the UIs being Gaussian distributed, if you sort of standardize them in that way, and you describe them with a student's T model, it would lead to the same, the likelihood function would then be the same as the profile likelihood that I had on the previous page, which you can just see by taking the log of this last equation. I realized that on the previous slide I had the log likelihood function, this is the likelihood. But anyway, you can just see that that works, I think, by inspection. So therefore, this is nothing new. It was certainly new to me, and I think it's new to a lot of the particle physics community. And I expect that for a large part of the sort of data science and statistical community is, oh, well, it's just students T regression now. It's just students T a constraint of the nuisance parameters. So here's the, I guess one of the most important use cases is in fitting a curve. And so let's suppose that the primary measurements are Gaussian distributed, and there's, let's see, independent, and there's n of them. And I want to fit some curve represented by this function phi of x. And the parameters in that curve are the parameters of interest mu. But I've allowed here also for a bias parameter theta I. Let me assume that the variances of the y sub i's, that they're known exactly. Those would be what we would typically just call the statistical errors of the measurement. And there's normally no big debate about their values. So let me assume that they're known. The u sub i's, these are then the auxiliary measurements that give me information about the bias parameters. All right, those I will model as Gaussian distributed with standard deviations sigma ui, and it's those sigma ui's that I'm calling the systematic errors, and those are the ones that are uncertain. So fine, the model as applied to this problem then gives let's see, I've first written down the case where these sigma ui's are known, and so that just gives me a sum of squares for my -2 log likelihood. So the type of fit that we would do is basically just a least squares fit, where we've got this additional set of terms to constrain the nuisance parameters. So, all right, and I realize now that in my slide, I've left out the slide where I say that I'm going to do this with the gamma variance model. But anyway, that leads then to the version where this quadratic term is replaced by the logarithmic terms, right? The same as I had a couple of slides ago. When you're doing the fit, you need then to also assess the goodness of fit. And the way that this would have been done in the normal least squares case is by looking at just the value of the sum of squares at its minimum. And that boils down to looking at the -2 times the log of the minimized likelihood divided by the minimized likelihood of the saturated model. And so again, that just gives you your normal sum of squares for a least squares fit. And in this gamma variance model, that sum of squares is replaced by the sum of logarithmic terms. All right. And asymptotically, that should have a chi-square distribution for n minus m degrees of freedom, where n is the number of measurements and m is the number of parameters of interest. Now, the problem is the following, is that statistic has a chi-square distribution if it's built up out of a sum of squares of Gaussian distributed quantities. But that's no longer the case because the sum of the quadratic term has been replaced by this logarithmic term. And so what happens is that when these error on the error parameters, the little ri's get a little bit too large, then the asymptotics breaks down. And so this is, I won't say that would be a showstopper, but I think a large part of the community would be reluctant to adopt this kind of a procedure if they suddenly realized that they didn't have a convenient measure of goodness of fit to use. And so I've tried to investigate a number of different ways around that. I've been collaborating with Alessandra Brazzale from Padova on using higher order asymptotics to define a statistic, which would then revert back to having something closer to a chi-squared distribution or an appropriate asymptotic distribution. And one of the things that I did investigate was some improvements with a Bartlett correction. And I'll show a slide in just a second about that. All right, so here is, for example, an example where I have two measurements, so n equals 2, and I'm imagining just fitting a horizontal line. And so if you looked at the statistic I defined on the previous page, if you assign to each of the two measurements only a 20% error on the error, well, that's pretty small. And so you see then a distribution of that statistic, which lines up pretty well with the asymptotic distribution, which in that case would be chi-squared for 1 degree of freedom. All right. If you had, on the other hand, R of 0.4, then you start to see marked differences. And particularly if you had a fairly poor measure of goodness of fit. So if the statistic Q came out to be quite large, then using the chi-squared distribution would then not give you a correct p-value. And so then on the right, it's just for a different number of measurements, but it's the same basic message. So what I played around with, and which worked reasonably well, was to take the statistic Q. You think it's supposed to follow a chi-squared distribution, but you see that it doesn't. And so you concoct this Bartlett correction. And for those not familiar, the idea is the following, is that I want this thing to look like a chi-squared distributed quantity, which has an expectation value equal to a certain number of degrees of freedom. So I define a new statistic equal to the desired number of degrees of freedom divided by the expectation value of the old statistic times the old statistic, so that by construction now, the expectation value of Q prime is equal to this number of degrees of freedom. That's the kind of mathematics that I would expect a physicist to do. That you say, all right, it doesn't have the right number of degrees of freedom, so just sort of scale it so it looks like it works. And it turns out that particular correction has a more legitimate, respected literature from Bartlett from the 1930s, who showed that not only does it get the right expectation value, but actually the distribution of the resulting statistic does indeed approach the asymptotic distribution more quickly. And so anyway, here's the Monte Carlo study that shows that. These are the same plots as from the previous page, but now of the Bartlett corrected statistics. So you can see indeed it agrees with the asymptotic distribution much better. All right, let me just flash back. That was without, that's with the correction. Now here I'm just going to flash.
And is there any intuition why that works so well?
Other than the fact that it gets the number of degrees of the mean correct by construction, no. All right, but why it actually works as well as it does, that's beyond me. And I would be keen to hear any sort of statistician's take on that. It does require that you determine the expectation value of the statistic. And for a very simple problem that I discussed in my paper, I was able to do that in closed form, at least approximately. But for almost anything past that most simple problem, you have to use simulation anyway. You have to use Monte Carlo to estimate the expectation value of Q. But that only takes, I don't know, 10,000 generated values. Whereas if you really wanted to, get a p-value way off in the tail, you might have to generate far more. So there is a definite savings in applying the Bartlett correction, but it's still maybe not as nice as you would like because it requires simulation. And so that's where Alessandra Brazzale comes in. And she said, oh, well, you should really just be using a higher order asymptotics as described in her book by herself, Davison and Reed. And so she defines, now I'm not going to try to explain because she's changed the notation on me, but she modifies the original statistic to a starred version of the statistic, which then approaches an asymptotic distribution, which for this particular statistic is standard normal. And then it approaches then plus corrections that decrease with increasing sample size. And here's some QQ plots that somehow illustrate that works. I'm not really prepared to defend the details of what she's done, and so I really would just want to flash this as an advertisement of the joint project that we're working on. But we do have the prospect of coming up with a statistics that will approach the asymptotic distributions very closely and not require any simulation. All right, let me go on. How am I doing for time? Yes, halfway through. All right, so here are a couple of examples. Here's one which I think is near and dear to the heart of most physicists, and that is you just have two measurements and you want to average them. So let's suppose that I have y1 and y2, those are my measurements, and the numbers that came out are 10 plus delta and 10 minus delta. And then I'll look at this for different values of delta. Now let me suppose that the statistical uncertainty of the measurement is 1. And then what I'll call the systematic uncertainty of each measurement is also 1. So that's the guy, the latter guy, that's the one that's uncertain. The statistical uncertainty, let's suppose that that's known, but it's this latter one that is going to be treated now as that's an estimate of an actually an unknown systematic error. And so what I've plotted here is the half length of the 68% confidence interval. So this is what the physicist would give as the size of the error bar. Right? And the way that I've determined the confidence interval is what in particle physics is called the MINOS method, which is a completely meaningless buzzword for most of the rest of the community. But I mean that you take the profile log likelihood and you move the parameter away from its estimate until it decreases, the log likelihood decreases by 1/2 times a particular chi-squared quantile that depends on the confidence level of the interval and the number of parameters of interest. All right, so here's what you get. And as for the size of that interval, as a function of the relative error on the error, and I've assumed that it's common to both. Just to be democratic, I assume that they are both characterized by a certain value of this little r parameter. And so first of all, let's suppose that the two values happen to come out equal, delta equals 0. So I'm averaging 10 with 10. And then what you see is that if little r is 0, actually all of the scenarios would give you an error bar size of 1. On the other hand, if the two values really are in agreement, then regardless of what you would assign for the little r parameter, it doesn't change much. And in fact, it even decreases a little bit if the two values line up perfectly. If delta's 1, so you're averaging 9 and 11, well, then it's actually pretty flat. But as soon as the values that you're averaging start to become quite discrepant, then you can see what happens is that as soon as you start to average, as soon as you would assume, say, a 20% uncertainty on the assigned value of the systematic error, then the width of the confidence interval jumps very quickly, right, to the point where it actually saturates. It's something related to the width, the distance between the two measurements. So this turns out to be important for the type of analyses that we do. It very often happens that we need to average two numbers which appear to be quite inconsistent. All right, so here's another example. Let's suppose that we're averaging 5 values, 8, 9, 10, 11, 12. And let's suppose that they all have statistical and systematic errors of 1. And in this plot here, I'm supposing that the error on the error parameter is negligible, 0.01. And I've assigned that value for all of the 5 measurements. Now, the way I've displayed this is that I've put for the inner error bars, that's what I call the sigma yi's, that's the statistical errors. And the outer error bars include the systematic error. So it's the quadratic sum of both. All right, so what do we get? Let's see. I'm averaging 8, 9, 10, 11, 12. So the average is obviously 10, all right? And the half width of the confidence interval turns out to be 0.63. Right there, by the way, is the p-value and the value of that Bartlett corrected statistic. Now, suppose, however, that measurement that used to be at 10, suppose it came out at 20. So we have an outlier. So now we're averaging 8, 9, 20, 11, 12. And so the average is 12. But because my error on the error parameter is still essentially 0, the width of the confidence interval does not react to the internal inconsistency of the input values. So this width of this confidence interval is still 0.63. All right, so that this outlier is pulling up on the average, because of course I'm describing it as Gaussian distributives, and the tails of the Gaussian are falling off very quickly. So it's pulling up on the average very hard. And that's what we would be doing prior to this error on error technology. Now, let me suppose that I assign a 20% value for this little r parameter democratically to all 5 measurements. And I suppose that they're in the configuration as they were before 8, 9, 10, 11, 12. All right, so the average comes out to be 10. The width of the confidence interval goes up a little bit. It was 0.63, and now it goes up to 0.65. Okay, so obviously I've included a new element of uncertainty, but it doesn't destroy it. All right, it doesn't change things very much. But now look what happens if I have the outlier. So I move that point that was at 10 up to 20. So now instead of having the average pulled up to 12, it only gets pulled up to 10.75. And furthermore, the width of the confidence interval gets inflated, as it in some sense should, because I have a bigger scatter between the input values. So I think both of those features would be regarded as good by most analysts. You want somehow the width of the confidence interval to reflect the fact that there's a bigger scatter in the values. And furthermore, you want the outlier not to have such a large influence on the average. So because this is now equivalent to a student's t likelihood, the tails are falling off more slowly, and so it doesn't pull as hard on the average. All right, how am I doing for time? Not too bad, actually. Let me go back and
20 minutes left. So yeah, if you plan to wrap up in like 15 minutes or so, then we have some time for questions.
Oh, probably less, actually. Maybe I've been rushing. I hope I haven't been speaking too quickly, but I sense now I'm actually going to finish on time, so that'd be great.
Oh, that's great.
So most of my colleagues, as I said, would have just said, all right, well, if the error bar is uncertain, then just inflate it a little bit. If you think that there's a 20% uncertainty in the value that you assign to some standard deviation, well, then just pump up its value by 20%. All right, so replace all the sigma ui's by sigma ui times 1 plus ri. Well, if you do that on the example that we just saw, then, okay, if there's no outlier, it of course gives you 10 still, and it then inflates the error because you've inflated all the error bars a little bit. They go from 0.63 to 0.70. On the other hand, if you do have the outlier, so that the value that was at 10 goes to 20, then of course the average gets pulled up to 12. And of course, because you're just doing a least squares average, the width of the confidence interval is oblivious to the internal consistency of the input measurements. And so you haven't really cured the problem, right? The sensitivity to the outlier is not reduced, and the size of the confidence interval is still independent of the goodness of fit. All right, so it is not sufficient to just inflate the errors. All right, those are sort of the toy examples that I played with in developing the model. This last summer, I had a chance to apply it to an interesting particle physics measurement. And this is a quantity called the anomalous magnetic moment of the muon, or what's called the muon G-2. And this is a quantity that has been in tension between measurement and theoretical prediction for a number of years. But just recently, there was another measurement that made the measured value quite a bit more precise than it had been previously. So here on the plot is the old measurement and the new measurement. Their experiment average is this purple point here. And then the prediction for this quantity from the standard model of particle physics itself has a substantial uncertainty because it has to be derived using perturbation theory to some limited order and using various types of mathematical approximations. So even the standard model's prediction for this quantity has a significant error band. Nevertheless, the tension between the green prediction and the purple measurement corresponded to a 4.2 sigma effect. And so that got lots of people excited. Within particle physics, if something goes over 5 sigma, we suddenly think we've discovered a new phenomenon. And this was 4.2, which is already looking pretty interesting. I don't know if some of you followed this, but what was a little bit, I don't know, surreal about this is that this was announced to great fanfare. And then almost immediately, another group came out and provided an alternative theoretical prediction, which was much, much closer to the experimental value. And so that this notion of a discrepancy went away almost immediately. But from where I sit, the current goal is the following: is I want to say, suppose we had a situation where there was a 4.2 standard deviation tension. This corresponds to a p-value of, I don't know, some 10 to the minus 6 or something. So let's suppose that you had this type of a situation, but I want to allow for the fact that the uncertainties of these error bars is itself uncertain. And in particular, the error bar assigned to the standard model prediction is going to be very difficult to assign an accurate value. It's just going to be some theorist's rough guess as to how much uncertainty there is in their prediction. All right, so this just summarizes the ingredients. There's the experimental value. I've adjusted the units so that it's 20.6 plus or minus 0.41, and the prediction is 18.1 plus or minus 0.43. And it's that 0.43 that is suspect. And the authors of that admit freely that they don't really have a good guess for what the error on the error is, but it could be substantial. All right. So that's what I've done. I've assumed that the number that they wrote down, this 0.43, is to be treated as an estimate of a true and unknown sigma squared on the standard model prediction, and that estimate is gamma distributed and characterized by some little r parameter. But it's not really for me to say what the appropriate little r parameter is. And so what I'm going to do is I'm going to show how that significance decays if you assume different values for the little r parameter. So I am in contact with the people who have produced the theoretical prediction, in particular Bogdan Malescu. And so we're trying to come up with a more well thought through statement of what the appropriate error on the error is. Okay, so the model in this particular case boils down to just having an ordinary quadratic term in the log likelihood for the measurement, because I'm saying that its variance is known, whereas I have this logarithmic term for the theoretical prediction. All right, so that's the thing I minimized to basically average well, it's going to give me an average of the prediction and the measurement. That's not interesting. What is interesting is the level of goodness of fit between them. Right? So the goodness of fit statistic then is the value of that quantity at its minimum. Now, I want to consider quite large values of little r, and so this is going to break the asymptotics. And so I've used Monte Carlo to get the distribution of the statistic. For certain regions, I've sped that up with a Bartlett correction. And okay, and then from the corresponding p-value, I get the significance, which I guess most statisticians would just call the z-score. I'm not sure what the terminology is, but in particle physics, this number of sigmas is what we would call the significance. And here's what it looks like then. There is the significance of the disagreement between the measurement and the theoretical prediction as a function of the assumed error on the error of the standard model prediction. And so if that's 0, it's 4.2 sigma. Now, what the black line shows is the prediction of my model. What the blue dashed curve shows is that if you just do this naive procedure of inflating the error by 1 plus little r. So in other words, if you just said, well, my error is uncertain, so I'll increase it. And you can see that at least for kind of small values of little r, that may lead to a very similar result. But as little r gets bigger and bigger, it's the significance decays much more rapidly with this gamma variance model, which I think is more realistic. All right, so that's, I don't know, is that shocking news to people who did the experiment? I hope I didn't shock people too badly. It's clear that if you include some new uncertainty, that of course this significance has to decrease. It doesn't decrease that much if you're only talking about a 20% uncertainty on the uncertainty. But for that theoretical prediction, frankly, 30, 40, 50% is not out of the question for the uncertainty on the assigned error bar. All right, so having that 4.2 sigma effect be actually a 2-point-something sigma effect, that's not out of the question. Here's what it would look like. The black curve is the same as on the previous plot. The blue curve is what happens if you cut all of the experimental uncertainties in half, but you keep the theoretical uncertainties the same as they were before. And so this is like if you redo entirely the experiment, but you don't alter the theoretical prediction and the values stay unchanged, then that 4.2 sigma discrepancy goes up a little bit. It goes up to over 5, but there's almost no gain if you think that that theoretical uncertainty has a 20% error itself. And then here's the gold curve is if you cut both the experimental and theoretical certainties in half. All right, so that's one application. I should now wrap it up. So the basic idea of this gamma variance model is that it gives confidence intervals that increase in size when the data are internally inconsistent, and it gives decreased sensitivity to outliers. And I think these were known properties of students t-based regression. And then the relationship between it and the students t model is that the number of degrees of freedom for the students t is 1/2r². I probably should have said that earlier at some point. And the basic idea is that the quadratic terms that would normally enter into the log likelihood are replaced by these logarithmic terms. So just some final comments. This method assumes that we can assign meaningful values to these little r parameters. And that means that you need to interrogate the experts who did the auxiliary measurements. Now, if the measurement is published and then the people who did the control measurements evaporate, then it's not so obvious that this is a useful approach. You might think, well, maybe you could take these little r parameters and try to fit them as well. And I tried playing around with that. I tried assigning, to be democratic, I assigned a global little r parameter to all measurements that you're trying to average. And I've put here future work, but let me say that I've played around with that enough to know that that's not easy. And if you look at the literature, you'll see that trying to fit the number of degrees of freedom of a student's t is a bit problematic, that it's just not entirely stable. The way that in the next comment, this is roughly what I've done with the mu on g-2 thing. I've used it essentially as a stress test. You say that you have a 4.2 sigma effect. Well, assume that your systematic errors that you used are not exactly known, and then start cranking up those little r parameters until your 4.2 sigma effect decays into a 2 sigma effect. And then ask yourself, are those values of the little r parameters realistic? You know, maybe you really don't know the values of your systematic uncertainties at that level. All right, and just finally, just to thank my collaborators here, Alessandro Brazzale. We're working together on the higher order asymptotics. My student Enzo and I are going to be applying this to measurements of the top quark mass. And then I'm working with both Bogdan Milescu on this mu on g-2. So I'll stop there. Thank you very much.